So in chapter 15, we're talking about gas mixtures, and there are a couple of important gas mixtures. One, of course, is air. Air is about 80% nitrogen, 20% oxygen. Another important gas mixture is when we collect gases over water. And so this is a way to generate oxygen gas. We have KClO3 here. The KClO3 decomposes with heat. So this triangle symbol again means heat. And so we're heating it up with a Bunsen burner here. You have to be careful because some things, as you heat them up, can potentially explode. And so in this case, a lot of pressure is generated, but we have a way to release the pressure by filling up this tube over here. And we'll have 3 halves oxygen gas generated. And so we're just going to form potassium chloride and oxygen gas in this. This is a redox decomposition here, in which chlorine, when we look at the oxidation states here, this is potassium chlorate. So oxygen's at a -2. Get a different, little narrower pen for this. Just use black. Oxygen's at a -2. Potassium is always +1. So we normally do potassium at first because that would just be a +1. What does that make chlorine? Everything has to add up to the net charge. The net charge in this case would be 0. And so what would chlorine's oxidation state be? Normally it's -1, but not in this compound. It's different here. So you would take -2 times 3 gives you what? -6. +1 gives you -5. It would be +5. Normally chlorine likes to be -1, and so that would be a good initial guess for chlorine's oxidation state. But in this case, if it's chlorine versus oxygen, oxygen wins. And so oxygen gets its normal charge, which leaves chlorine on the short end of things. And so chlorine's not very happy. And so what's going to happen is if you heat this, then chlorine's going to strip electrons off oxygen. And so over here, potassium is +1, which makes chlorine what? -1. +1 minus 1 equals 0. Oxygen's going to be what? 2 times what gives us 0? 0. Oxygen's 0. So essentially chlorine's going to take the electrons from oxygen in this particular reaction here. And this leads to the decomposition of potassium chlorate. But the potassium chlorate wouldn't be expected to be all that particularly stable because of this high oxidation state, we'd call it, on chlorine. Chlorine's quite electronegative. But as we heat this, something like this, you got to worry about explosions. But as we heat this, it's not explosive. Somebody already tested this out. In fact, it's a little bit slow. Since it's a little bit slow, they actually add MnO2, manganese 4 oxide, as a catalyst. Catalysts speed up the reaction, So they aren't actually consumed in the reaction, but they help speed things along. So where does the oxygen gas go? Well, the oxygen gas, if we're just contained in this tube, the pressure would go up, as we generate more. That could lead to a pressure explosion. But there's a hole in this stopper here, and the oxygen can leak out the hole and go into this tube here. Initially, there's air in this tube here. The air's still there. Now, this big tube here was originally all filled with water. It's like a test tube. It's a big test tube. So what you do is you fill this big test tube with water, and then you cap the end of it and flip it upside down, and then put it into this container here. And so this whole thing was filled with water. This. And it's upside down. So as the oxygen is being generated, it's collected via water displacement. The oxygen is going to rise here. As the oxygen rises, it's going to collect at the top here, and it's going to push the water down. We want to get the water down to a particular level here. The level we're going to get the water down to is the same as the water level outside the container. And so we're going to fill this entire tube with oxygen here. Like this. But the problem is this tube isn't entirely filled with oxygen. There's also water vapor. That is, water evaporates and creates humidity. So there's some water vapor in here as well. And so this is actually a mixture, and this mixture we call wet oxygen. And it depends on the certain circumstances, but scenarios where it could be saturated with water vapor or unsaturated. Eventually it's going to become saturated. It depends on how much water that we have in the reservoir. And so what happens is water evaporates, and then there's going to be a limit, because what we're going to have is we're going to have two processes occur. One is called vaporization, where the water vaporizes. The rate of the vaporization depends on the temperature. So the higher the temperature, the more water vaporizes, and it just evaporates faster. The lower the temperature, the less water vaporizes. But when we hit something called saturation, we can have the reverse process occur. And the reverse process is called condensation. And so what we do is we have two processes occurring here. One process is the vaporization of the water, or evaporation. And so that's going to generate more water molecules in this. But what happens is, as soon as you get water molecules in the vapor state, they can come back and contact the water and get stuck. And so the waters can come back and condense back into the liquid state. That is, they get stuck with the liquid here. And what happens when we have 100% saturation, we call it relative humidity, 100% relative humidity. What we have is that the vaporization rate is equal to the condensation rate. And we say that the gas is saturated with water vapor. The situation outside the container here is different. Outside the container, we have the evaporation rate, but the condensation rate is much slower. The level of humidity. Have you been in 100% relative humidity before? No, I mean, like, what's comfortable? Maybe like 50% humidity or 40% relative humidity? When it gets over 50%, it starts getting muggy and uncomfortable. And if it were 100%, it'd be extremely uncomfortable. So the environment inside the tube is like an indoor swimming pool. An indoor swimming pool, when you go into the room, it's really humid. It's really humid because it's been saturated, the air's been saturated. But outside, An outdoor swimming pool is like this situation where it never becomes saturated because the atmosphere is just too big to saturate. And eventually the swimming pool will evaporate completely and you'll have a dry swimming pool. But if you enclose it into like a test tube, the swimming pool, then you can saturate it. Depends on how much air we have to saturate it. And so in this case, there's plenty of water here in the reservoir such that we can saturate the gas here, and that's what's going to happen here. This is called the equilibrium vapor pressure, and once we hit this equilibrium vapor pressure, it doesn't change. Equilibrium means there's no change, kind of thing. Equilibrium vapor pressure. It's called vapor pressure because this pressure is generated by the vaporization of a liquid. And that's what we have here. Now, we call it 100% relative humidity because the humidity changes with temperature. So at higher temperatures, you can get more water, and it'll become more humid. But it still becomes saturated. At lower temperatures, the saturation limit is much lower because the rate of vaporization is quite a bit slower. And so the vaporization rate, once we hit saturation, the vaporization rate is equal to the condensation rate. That's what these two arrows are trying to show. These two arrows are showing they're the same. Whereas over here it's unsaturated. In this particular situation, we have unsaturated, and we have less than 100% humidity. Now, it's interesting, it doesn't matter the size of this container, the pressure of the water generated is called P vape. And so the equilibrium vapor pressure is given the symbol P sub vape. And P vape is a function of temperature, depends on temperature only. It doesn't depend on the size of the container. So if I had a bigger container here, the saturation vapor pressure is going to be the same. That means more water has to vaporize, essentially. And so it depends on T, not on V. Well, this makes things very handy for us because when we have a mixture like this, then the pressure of the wet oxygen, actually, let me do this in black maybe. We visualize this using Dalton's law. The pressure of the wet oxygen is equal to the P total, which is equal to the pressure that's generated by just the oxygen molecules, O2, plus the pressure generated by the H2O. This is the vapor pressure of water. The vapor pressure of water we look up in a table. It just depends on temperature, so we'll have a vapor pressure versus temperature table. And we can take a look at that. Let's see. So typically, when we look at the vapor pressure of water, it's given in a table such as this. Let's take a look at this table. Yeah, it's fine. I'm going to copy this. And then let's go ahead and insert slide. So I just look it up here. This is the vapor pressure is in units of torr. So let's say I'm at 25 room temperature, here 25.0, the vapor pressure is going to generate 23.756. Now what happens to the vapor pressure as I increase the temperature? As you increase the temperature, the vapor pressure rises or lowers? It rises. Why does it rise? It's as you increase the temperature, what does evaporation happen slower or faster? Evaporation. Faster, that's why. As you cool down the temperature, what happens to the vapor pressure? It decreases. So a table like this, we don't really worry. When I look at a table like this, I just look at the extremes. The extremes aren't that wide of a range. This is a very narrow range here. It just goes from 19.1, where we're at about 16.5, to 31 here, where we go to about 33.695. So it doesn't really change all that much. It's still fairly low, you know. But that's just due to water evaporation. Now, what we can do is we can try to visualize this. You know, when you look at this, it just looks like a bunch of numbers. So in science, what we try to do is do the process called data reduction. And you got a bunch of numbers here. It's hard to visualize that, and so we try to reduce this into easier to digest forms. One of the easier to digest forms is by graphing it. And so let's see what the curve looks like. This is off Wikipedia. Oh, this might be better here. This gives a more extensive range. This shows the vapor pressure of water from 0 degrees Celsius to 100 degrees Celsius. Note the vapor pressure here. As we go from 0 degrees Celsius, the vapor pressure is quite low, 4.58 torr. Very low. You wouldn't expect much evaporation or vaporization occurring. When we hit 100 degrees Celsius, this is very interesting. What is the vapor pressure in torr? Almost 760. In fact, it should be 760, because if you look at it in atmospheres, it's 1 atmosphere. So that means a torr, it's not exactly 760 in 1 atmosphere. Basically, 100 degrees C, the vapor pressure is 1 atmosphere. So that means that the pressure of the water vapor that's being generated is 1 atmosphere. What happens at 100 degrees Celsius to water? Yeah, it evaporates so fast that we don't call it evaporation. We call it what? At 100 degrees Celsius, 212 degrees Fahrenheit, what happens to water? It boils. Boils this process of this vaporization, which happens quite quickly. And so we get boiling occur. Let me shrink this down a little bit. So we call this the normal boiling point of water. So let me add that in here. Oops. Now it's working. So at 100 degrees Celsius, the vapor pressure of water is equal to normal atmospheric pressure. And therefore, this temperature equals 100 degrees C, is called the normal boiling point of water. Well, if that's a normal boiling point of water, what are the abnormal boiling points of water? Well, the abnormal boiling points of water are when the atmospheric pressure is not 1 atmosphere. So let's say you're in Denver, Colorado. You know, Denver, Colorado is a mile high, called mile high. And at higher elevations, like a mile up in elevation, you're going to be in a thinner atmosphere. The thinner atmosphere is going to weigh less. And so let's take a look at atmospheric pressure in Denver. Well, actually, it's kind of high today. Let's look at the average atmospheric pressure. 24.9 inches. I don't want it in inches. Average atmospheric pressure in torr. They don't give me it in torr either. 0.85 atmosphere seems quite low. Okay, 24.9 inches. I'll just convert it into millimeters. We'll just take this data. It's from Pearson. So that's from our book, actually. 24.9 inches of mercury. So we go 24.9 inches, and then how many centimeters per inch? Times 2.54 centimeters per inch, times 10 millimeters per centimeter. And so it's 632. Actually, it was here. 632 millimeters. 632 millimeters is about 632 torr. So if we're at 632 torr, which is about here, somewhere around here, do you guys know about linear interpolation? Have you had to interpolate in math? No. All right, then what we're going to do is we're going to graph this data. When we graph this data, here, let me put it over here. Oops, not that. Oops, why didn't it copy? Try it one more time here. There are different ways of visualizing it. So we just determined the average atmospheric pressure in Denver is 632 torr. So this is just going to be a rough estimate. So we'll go to about 600, 10, 20, 30. So we'll go about 630 here. Try to go up here to here. I can't draw a straight line. Having difficulty. And then we'll go across here. Ah, shoot. Look at the units they use for this pressure in kilopascals. Why? Oh, actually, we're okay. They have kilopascals here, so we're all right. So we're at 18,000, about 18,300 kilopascals. So let's go to 18, or is that 18 point? Yeah, 18.3 kilopascals. It's about here. So this is about, let's say 16, this is about 20. So between 16 and 20 is about halfway. So we'll just say about 58 degrees roughly Celsius. So under normal atmospheric pressure here, we would require, what's the temperature? This is an odd temperature unit. Yeah. Actually, this is not a good curve here off Wikipedia. This is better. So this is off. I should probably cite the source of this if I'm going to include it in this. Oh, this is probably a little bit better here. So it's normal atmospheric pressure is 760. So in order for the vapor pressure to cause boiling, the vapor pressure has to equal the atmospheric pressure, and then we have boiling occur. And so under normal conditions, boiling water occurs when the vapor pressure of water is equal to the atmospheric pressure. Normal atmospheric pressure is 760, and so the vapor pressure of water is 760 at 100 degrees C. But in Denver, the atmospheric pressure is less, and so in Denver it was 632 millimeters of mercury. And so if we go to 632, then water boils at about 95, let's say, degrees C. Here. Roughly. This is just a rough estimate. And so, excuse me, if water boils at 95 degrees, then let's say if you're at sea level, you're boiling pasta at 100 degrees C, versus if you're in Denver, you're boiling pasta at 95 degrees C. What do you think is going to cook faster, 100 degrees C or 95 degrees C? 95. It's going to cook faster? Or higher temperature cooks faster, or lower temperature cooks food faster? Higher temperature. And so, I don't know if they still do this, but on cooking, like cookbook instructions, they have high altitude versus low altitude. At high altitudes, you just have to cook it longer, a lot longer. The pressure on top of Everest is about 1/3 of an atmosphere. And so if you're about 1/3 of an atmosphere, what temperature does water boil, let's say? So if let's say it's 800 and divide that into 3 portions, it's going to be at 200 and something. So water is going to boil about 60 to 70 degrees Celsius. Is your pasta going to cook very quick then? No, it's not. In fact, you could get water to boil. Have you ever seen water boil at room temperature? In order to get water to boil at room temperature, all you have to do is you have to lower the atmospheric pressure. How do you lower the atmospheric pressure? The way you lower it is by using a vacuum pump. And so there are different types of vacuum pumps you could use. There's one with a hand crank vacuum pump, but this is, we'll just go with this one.
Boiling point of water because we are at 1 atmosphere of pressure. This water is currently
Turn off
20.
the audio. So the water's at 21.6 Celsius. And then they put this cover on here, and then you can see a vacuum tube out here. And so they're just going to suck the air out of here. When they suck the air out of here, it lowers the pressure in here. This has to be a strong container, otherwise it can implode. Let me speed this up. Depends on how powerful the vacuum is. And so now what's happening is the pressure of air inside here is being reduced. And when we get the pressure of the air inside here to about 25 torr, then water will start to boil. So we can see water boiling at 21.6. Actually, they have to get a little bit better vacuum at 21.6. And then release the vacuum, and then it stops boiling, and then they can check the temperature again. And so the boiling, all we have to have for boiling is that the atmospheric pressure and the vapor pressure are equivalent. And that's going to, atmospheric pressure changes, therefore we have the normal boiling point and then all the other boiling points. Now, this curve extends up here, so we could have vapor pressures higher than this, as the temperature grows higher. And it's not so easy to do because water automatically boils at 100 degrees C unless you put the water into a pressure cooker. If you put the water into a pressure cooker, then we can get temperatures higher than 100 degrees C for the water. And so a pressure cooker cooks food even faster than normal because we can get higher temperatures. And in cooking, they say that for every 10 degrees C temperature increase, the cooking speed gets cut in half. And in other words, you'll cook the food twice as fast. So, going back here, this vapor pressure of water, we can just look up in the table. There's no problem with that. Here's our vapor pressure table. And then we can calculate the pressure of the dry oxygen. What we have here is this. We need the water level to equal. So this is why they're saying water level of tube is equal to that of the pan. And so what that means is that the weight of the water inside this is equal to the weight of the water outside this. The water levels are equal. Do you remember doing this? And that's called equalization of pressures. So in other words, the pressure of the wet oxygen is equal to the pressure of the atmosphere. The wet oxygen is pushing down on the inside water level. The atmosphere is pushing down or weighing down on the outside water level. And when the two water levels are equal, then the pressures are equal. The pressure of the wet oxygen consists of the pressure of the dry oxygen plus the pressure of the water vapor. And that's going to equal the atmospheric pressure. And therefore, the pressure of the dry oxygen, the pure oxygen, is just equal to the atmospheric pressure minus the pressure of the water vapor. And so we can calculate it. Now the pressure of the dry oxygen is going to be less than this because what we're doing in Dalton's law is we're looking, this would be the volume of the dry oxygen here, and if we remove the water out of there, there's going to be fewer collisions in there. And so the pressure of the dry oxygen over here is going to be less. And if we add up the two pressures, the pressure of the dry oxygen plus the pressure of the water vapor, then we get the total pressure here. So this would be Dalton's law. We could also visualize this according to Avogadro's law. Now, if we visualize this according to Avogadro's law, what we do here is something a little bit different. And what we do here is we segregate it. And so what I'll do here is I'll put all the water vapor on one side here. Let's put all the water vapor on the bottom of the tube. And then I'm going to put the oxygen on the top of the tube. And so in Dalton's law, if I put all the oxygen up here, I'm going to get this volume of oxygen. And then I put all the water vapor down here, I'm going to get this volume of water vapor. And so with Dalton's law, what we have is this. We have that the volume of the dry oxygen plus the volume of the water vapor is equal to V total, the total volume. That's it. Now, we can figure this out because we have the fractions and percentages. So the mole fraction is always the same. So n sub A over n total. But it turns out the mole fraction is going to be the same as the pressure fraction, PA over P total, which is going to be the same as the volume fraction, VA over V total. So I'm going to calculate the percentage. Or the pressure fraction over here. So it depends on the temperature here. Let's say we're at 25 degrees C. Then we can look up the vapor pressure of water. The vapor pressure of water is 23.8, let's say. I'm going to round it. 23.8 millimeters of mercury. Let's say normal atmospheric pressure was 760. So I'm going to say we're at normal atmospheric pressure, which is 760 millimeters of mercury. And therefore, what is the pressure of the oxygen? The dry oxygen. Comes out to 736.2 millimeters of mercury. These two have to add up. And that's it. And so let's go with the pressure fraction of the water vapor. The pressure fraction of the water vapor is 23.6 out of 760. And I'm going to convert the fraction into a percentage. So let's go ahead and convert that to percent here. So 23.6 divided by 760 is only 0.47, 0.5%. Say 0.473%, 474%. So I'm exaggerating this, overly exaggerating. It's only about 0.5% water vapor in there as far as the pressure is concerned. And then 736.2, let me make sure I did that right. 736.2 out of 760 total times 100%. So 736.2 divided by 736.2 divided by 760. 96.87%. 96.87%. So we have about, I don't know, these should add up. I think I screwed up my calculation here. It's got to add up to 100%. And so something's off. Let me double check this. 23.6 divided by 760. Oh, 3.1. I messed up that calculation. So this should be 3.1. 1%. They don't quite add up to 100% because of rounding error. I was a little overzealous in my rounding. But it's close, 99.98. So let's do the rounding error. So in other words, 3.1% of the pressure is generated here. Is from the water vapor. And also 3.1% of the volume. If we look at it in terms. And so if we take 100% of the volume, then 96.9%, will be oxygen. And 3.1% will be water vapor. And the same thing with the pressure. 96.9% of the pressure is going to be oxygen. And the same thing with the moles. The moles will have 96.9% of the moles, or that is, moles or molecules. So out of every 100 molecules, 96.9 of those will be oxygen. 3.1% will be water vapor. And so this gives us different ways of visualizing this. And that's because the mole fraction is the same as the pressure fraction, which is the same as the volume fraction. And so we could visualize this using Avogadro's law, Dalton's law, or just the molecules as the fraction, percent by mole. All right, so this is a topic that's covered in gases, in chapter 15. And the calculations are very simple for Dalton's law, so this was an example calculation we looked at last time. And then we had some comparison of properties of liquids and gases. Gases can be compressed. They can be compressed because there's empty space. Liquids cannot be compressed. When we look at liquids, liquid molecules are touching one another. And so we can see that here in this visualization here. And so if I look at gaseous water vapor, there's a lot of empty space there. But when I look at the liquid itself, the liquid water molecules are all touching one another. And so there's no more, or not much more space available. So liquids are incompressible. That leads to hydraulics, hydraulic lift and that kind of stuff because of the incompressibility of liquids. Gases expand to fill their containers. Liquids do not. Liquids just sit at the bottom of the container. Gases have low density. Liquids have high density. Gases are about 1,000 times less dense. And so what that means is we use different units. For gases, it's inconvenient to use grams per milliliter. Instead, we use grams per liter. Because if we use grams per milliliter, it would be like 0.001. 0.001 is a hassle. 0.001 is 1 gram per liter. That's much easier. Whereas liquids have about 1,000 times more density. So liquids will have grams per milliliter, whereas gases will have grams per liter. Gases may be mixed in a fixed volume. Liquids cannot. Yeah, it's easy to add more gas. Of course, the pressure is going to go up. So if we add more gas to this tube, there's space, but the pressure, it will climb because we'll get more collisions. With liquid, you can't really do that. You need more volume. Gases exert constant pressure on the walls of the container uniformly in all directions. It depends on how big the container is. If you have a container that's as big as the Earth, then no, it's not, necessarily because of gravitational settling. But if the container is not the size of the Earth, then you'd expect it to exert equal pressures. Whereas liquids, pressure increases with increasing depth. And so the deeper you go here, the heavier it gets. Air does the same thing, but you have to go very deep in air. We were talking about Denver. Denver, the atmosphere is thinner, and so the pressure exerted at the top is lower than the pressure exerted at the bottom, sea level, if your container is that big. But it's not usually that big. And so if we have a container this big, then it doesn't matter. The gases can collide with all surfaces, bottom, sides, and top, with equal frequency and strength of collision. All right, then the slides go to properties of liquids, but before that, I do that, I'm going to talk about gases, liquids, and solids. So let's start off with a solid here. Now, a solid, we have different kinds of solids. Solids can be atoms that are held together, or molecules, or ions. And so we're going to have particles that are held together. And these particles are going to be made up of atoms, ions, molecules, or atoms. I should maybe go in some order here. And so let's go in this order. Atoms, molecules, ions. Now we're looking at the force holding the atoms, molecules, and ions together. And so what is the force that holds these things together to make a solid? And the force is going to be either bonds. We could have covalent bonds. We could have ionic bonds. We could have metallic bonds. Or they could be what we call IMF. IMFs. IMF stands for interparticle or intermolecular forces. Inter means between. Whereas intra means inside or within. Now, these don't have to be molecules. These could be other things as well. And so molecules in this context doesn't always mean molecules. Molecules in this context actually means particles. And the particles are going to be atoms, molecules, or ions. And so IMFs are typically weak, and these are strong. Weak. So some solids are easy to break apart. Other solids are more difficult. But what we can do is we can heat these up. And so in a solid, what we say is that the forces, the forces that hold this together are stronger than the kinetic energy, than the temp. Temp is basically kinetic energy. Kinetic energy is what again? Motion, right. And so the temperature is not enough to break this solid apart. But what happens if we increase the temperature? The solid melts into a liquid. So in a solid, the forces are greater than the temps, the forces holding it together. Whereas in the liquid, the forces are approximately the same as the kinetic energy, KE. I'll abbreviate here. And so what happens is that we end up having translational motion here. This is usually crystal or glass. Glass is non-crystalline, amorphous, we should call it. Crystal or amorphous. When we go to a liquid, we have translational motion now. But the particles are still stuck to each other. And so the forces holding them together are comparable to the kinetic energy. And so they can translate. But the particles are still held together. If we continue to increase the temperature, the liquid is going to get converted into a gas. Here, the forces that hold the particles together is going to be weaker than the kinetic energy. It can go. Excuse me. So we've talked about bonds already, covalent, ionic, metallic, but we haven't talked about IMFs yet. And so that's what we're going to do next. We're going to talk about IMFs. And so I'm going to rearrange the order of these slides because I want to talk about IMFs before I talk about liquid. Properties. So, molecular, I'm going to put in quotation marks because these are the forces between, it doesn't have to be molecules. It could be atoms as well. It also could be ions. But normally ions like to form an ionic bond, but sometimes we get something weaker. So for example, in molten salts. If we look at a molten salt, the ions are still held together, but it's not a bond. It's just an intermolecular force, that is, the force between the positive and negatives. And so IMFs are electrical forces that hold the particles together. Let's call them electrical attractions. That's what IMFs are. And these electrical attractions, sometimes they're easy to see, sometimes they're more difficult to see. But normally we have polarity. Polarity means they're usually a dipole. Sometimes we can have monopole. Do you know what a dipole is? A dipole is two poles. A monopole is one pole. And so a dipole is going to have a positive end and a negative end. This would be an electrical dipole. A magnetic dipole would have a north pole and a south pole. And so molecular polarity, we have a dipole, a positive end and a negative end. Or a monopole. A monopole would be like, chloride. It's just negative, or sodium, which is just positive. The chloride would be a negative monopole, the sodium would be a positive monopole. These are two different monopoles. We also worry about size, because size, the more concentrated will have a greater charge density. And so we worry about charge density. Well, anyway, we get to a dipole force. There's an interaction between positive pole of one polar molecule and negative pole of another. It's a dipole force. This should have been in blue. The dipole force. We have something called the induced dipole force, or the London force. Induced or London force. The induced dipole is a weak electrical attraction between molecules temporarily produced by shifting of internal electrons. And this is kind of not very descriptive of an explanation. So what I call this instantaneous dipole, induced dipole attraction. And so we'll look at that in more detail. And then we have hydrogen bond. Hydrogen bond is not really a bond. It's not a covalent bond, it's not an ionic bond, it's not a metallic bond. What it is an IMF between hydrogen in one molecule and a highly electronegative atom in another polar molecule. And this would be the strongest intermolecular force. And so this is an unusually strong dipole. Now, even though it's one of the strongest intermolecular forces, one of the strongest intermolecular forces, it's still much weaker than a covalent bond. So it's about 1/4 of the strength of the weakest covalent bond. One quarter of the strength of weakest covalent bond. So covalent bonds still a heck of a lot stronger, even the weakest ones. The weakest covalent bond is about 100 kilojoules per mole, and the hydrogen bond is about 25 kilojoules per mole, so only about 25% of that. So the dipole force, we have permanent dipoles. So for example, bromine chlorine is an unusual molecule. This is bromine chloride. Monobromine, monochloride, but just bromine chloride. Chlorine's more electronegative. It's closer to fluorine. Bromine's less. So one end of this is positive. The other end is negative. The negative end, they usually use red, and the positive end, they use blue. So that's going to be attracted to this blue here. This red here will be attracted to that blue. And this red here will be attracted to this blue here. And this red here will be attracted to this blue here. And so these would be our dipole. These are permanent dipole interactions here. And so this is what we call dipole-dipole attraction. Each of these molecules acts as a little dipole. And so what happens is the electron cloud gets polarized towards chlorine. And this asymmetric electron cloud causes this charge to show up. Bromine chloride's neutral, since the amount of negative charge is generated is equal to the amount of positive charge. But anyway, we have a positive negative attraction. So this positive being attracted to this negative being attracted to that positive, and that's positive. And this positive being attracted to this negative, and this whatever negative we have there. They're showing the force of the attraction using this, colored area here. There's going to be, and that's what causes these to become sticky. Now, at room temperature, bromine chloride is a gas, so it's not very sticky. These molecules are easily broken apart. It's gaseous. In order to get it to liquefy, you have to cool it down quite a lot. And then it'll eventually liquefy. That is, the molecules will stick to one another. And so we're looking at different degrees of stickiness. The stronger the dipole-dipole attraction, so the stronger the dipole-dipole attraction, the higher the boiling point. And therefore, if it's gas, then we're going to, it can condense at higher temperatures, excuse me. If it's a liquid, it'll boil at higher temperatures. The weaker the strength, the lower the boiling point. So this gives us a quick way to get a judge of that. If the boiling point's above or below room temperature. If the boiling point's below room temperature, we have a gas. If the boiling point's above room temperature, we have a liquid. So let's take a look at this. If we look at nitrogen, look at its boiling point. It's below room temperature, which means nitrogen is a gas. However, if we look at bromine, bromine's boiling point is above room temperature, which means bromine is either a liquid or it could be potentially a solid, as well. But it turns out bromine's a liquid. ICl is also a liquid. This table is trying to show two things. One thing is the dipole makes it higher. So this is nonpolar nitrogen. Carbon monoxide is polar. So what do you expect to have a higher boiling point? We expect carbon monoxide to have a higher boiling point because it has dipole-dipole attractions. And it does. Minus 196 versus minus 192. It's higher. But is it all that much higher? Barely, right? Silicon tetrahydride or silane, this is nonpolar. This is polar. Look, the polar molecule has a higher boiling point, minus 112 versus minus 88. If we look over here, nonpolar versus polar, the polar one is going to have a higher boiling point. This, 59 versus 97, 97. So the polar one has a higher boiling point. But the situation is this. The reason this chart is so convoluted is because in order to get a fair comparison, the two molecules have to have the same number of electrons. And so to make a fair comparison, the molar masses, or molecular masses, molecular and molar are slightly different. are a bit different. The molecular masses are the same, are roughly the same. So the only comparisons we make are in these little boxes here. So we're not going to compare, let's say, polar ICl to nonpolar N2. This would not be a fair comparison because the molar masses are quite different. And so we don't compare these here. Otherwise, it becomes too difficult. And so that would not be a fair comparison. Now, why is that? Why that is because of another type of intermolecular force. So when I compare this, look at, there's barely any difference between N2 and CO. You see that? Why does N2 have such a high boiling point compared to CO? You know, you'd expect CO to be much, much higher. And the reason is because the forces, the IMFs here, are going to be a combination of two. We have London forces. London forces are always present. Plus dipole forces. Dipole forces are not always present. These require a polar molecule. And so what we see is the baseline. Let's say the London is giving it a minus 196. Well, that's going to be 4 degrees higher due to the dipole. Let's say the baseline here is minus 112. And this is going to be higher by 40, roughly, etc. And so this is not a fair comparison because London forces depend on the number of electrons. The more electrons, the stronger the London force. I'm just going to call it London force because it's easier. You could also call it the induced dipole force, or you could also call it the instantaneous induced dipole. I call it the instantaneous induced dipole because that's the most descriptive. There's two nonpolar atoms or molecules here. What happens is we get an instantaneous polarization. This is very short-lived. This is called an instantaneous dipole. The electron's always moving. And so averaged over time, the electrons here are just all over this, evenly distributed. But once in a while, there's more electrons up here. Let's say both of these electrons move to the top, left. That leaves a deficit of electrons here. But the electron's always moving, so this disappears. And so we call it instantaneous because its life is very short. It's fleeting. One moment it's there, the next moment it's gone. But in the short moment it's there, what it does is it induces a dipole in the adjacent atom or molecule. And so we call this an induced dipole. So if both electrons are here, that means there's more negative charge there. The other electrons aren't going to like that. And so what's going to happen is the electrons are going to try to stay away. And so that's going to induce these electrons to move, setting up another dipole here, you can see. And then we get the London force. The London force is also a short life. This is short life. But it's long enough that, and it constantly forms and reforms. So even if it's a short life, there's a new one that's forming. And so there's a constant forming and the opposite of forming. What is that? Disforming? Disforming? I don't know. In other words, they appear and disappear continuously, but overall, they result in an attraction, net attraction. So anything with electrons can do this, and so we have both. Hydrogen bonds are very strong permanent dipoles. And so here we'll see some hydrogen bonds aren't technically real bonds. So let me put that bonding in quotation marks. But it's when hydrogen needs to be bonded to nitrogen, oxygen, or fluorine. And so this is our requirement. Requires that H be bonded to N, O, or F. Why those three? Because this is the most electronegative. This is the second most En, electronegative, and this is the third most En. And so what happens is that creates a dipole. The biggest dipole we're going to create is with HF. And then the next biggest would be with HO. And then the smallest of these will be with HM. But even though the HN is small, these three are all bigger than everything else. And what that's going to result in is a strong hydrogen bonding interaction. And so that means this hydrogen over here is going to be attracted to this nitrogen over here. And this hydrogen here is going to be attracted to this oxygen here. And the fluorines and the hydrogens attract here. They're hydrogen. Hydrogen bonding is important in biological systems, of course. This is what holds DNA in its helical structure. And so hydrogen bonds are extremely important in so many things. But overall, these are the strongest. Although the London forces can be stronger if you have a big molecule. Big molecule has a lot of electrons. A lot of electrons can generate big instantaneous dipoles. Let me talk about that briefly here. If you have only 2 electrons, you'll get dipoles like that. But let's say you have a big atom with lots of electrons. Let's say you have 20 electrons. If you have all 20 electrons going to one side of this in one instant, then it's going to generate an enormous instantaneous dipole. And so the greater the number of electrons, the greater the London force, and the greater the boiling point. Helium has an extremely low boiling point. It only has 2 electrons, so the boiling point of helium is 4 Kelvin. Versus xenon. Xenon has a much higher boiling point because xenon has a lot more electrons. And so it's going to be much, much greater than 4 Kelvin boiling point. It's 54 electrons, I think. 54 electrons is correct. We can kind of get an idea of it here in this particular graph. This is just showing the unusual strength of hydrogen bonding. Carbon hydrogen is no H bonds. But ammonia has H bonds. And water has H bonds. And look what happens to the boiling point. This is the boiling point. Boiling point is unusually high because if you extrapolate this curve out, it should be here and here. But it's way up here. Way up here. These are increasing polarity. And this trend here is increasing number of electrons. So as we go further to the right, we have increasing London force. And when we look at a square like this, or a rectangle like this, then it's polarity changes. So the highest within the rectangle is the most polar. The number of electrons are the same. They use molecular mass because the bigger the molecular mass, the more electrons they have. I use number of electrons because molecular mass is not due to weight that causes them to boil at higher temperature. It's due to London forces. All right, let's take a break here. And then we're going to finish up this chapter shortly. Were you guys prepared today for a retake of the nomenclature? Yeah? Sure.
I didn't get my test back yet.
Okay. You didn't get yours back? Let's see what I'm going to do. Anybody else prepared? You could retake it. Maybe we can postpone the retake, and unless Sheila, you can take it. All right, so we're going to look at our some properties of liquids. So we already talked about one of the properties, vapor pressure, and equilibrium vapor pressure. And so let me bring up this slide here, I think. So if we have an enclosed container like this, then we could saturate the gas above the liquid. So there's some water here. And so the air that's trapped in here can get saturated with water vapor due to this. This process, when it leaves, is called, well, the water breaks off the surface, we call that. No. Mm-hmm. Surface of liquid. All the water molecules are moving at the same speed. So some have higher energy. These ones that have higher energy can break off the surface. Both of them are kind of stuck down here. This is called vaporization. So vaporization. Eventually we hit this point. You know, the vaporization rate just depends on the temperature. So the number that vaporizes is kind of fixed by the temperature. But the number that condense depends on how many we have up here in the vapor state. And so here we have one condensation, another. So we have 3 vaporizations, 2 condensations. When we get enough water vapor molecules, then we'll get 3 vaporizations and 3 condensations. When we have 3 vaporizations and 3 condensations, we hit a state of what's called dynamic equilibrium. Dynamic equilibrium, I'm going to move this slide out. is shown here. This is non-equilibrium. So this is dry air. Let's say there's 0% humidity. Completely dry air, we're just going to have evaporation occur. There's no condensation because there's no water molecules in the gaseous state. But once we start getting water molecules in the gaseous state, then we're going to have condensation. But the rate of condensation depends on how many gaseous water molecules. The fewer there are, the lower the condensation rate. So there aren't that many here. So the evaporation rate's greater. And so this is less than 100% humidity. Maybe that's like 10% humidity. And then as we get more and more water molecules, the condensation rate increases. But it's still, we have net vaporization. And then we're going to grow. Here we have net vaporization. But once we hit this point, we have so many water molecules here that the condensation rate, this arrow, is equal to the vaporization rate. And so for every 3 molecules that vaporize, 3 molecules condense. And so what that means is that there's no change in the humidity. We've saturated, and so this is the most humid it can get. And this would be 100% relative humidity. It's going to stay that way indefinitely. So this is what we call a dynamic equilibrium. Equilibrium means there's no change. So there's no change in the humidity. But it's dynamic because the water molecules are constantly cycling, you know. And so 3 will vaporize, 3 will condense. And so that's constantly occurring, and that's called the chemical exchange process. And so we hit this state of equilibrium or dynamic equilibrium. Dynamic means change. Equilibrium means no change. So it's dynamic at the particulate level, but it's an equilibrium at the macroscopic level. That is, it's 100% humid and doesn't change. So vapor pressure of water is important. And vapor pressure is going to depend on the IMFs. The stronger the IMFs, the lower the vapor pressure. Why? Because if the water molecules, you know, water molecules have a certain stickiness to them. But there are other molecules that have more or less stick to them. That is, there are excuse me, molecules that have even stronger intermolecular forces than water, like glycerin, and it's like a syrup. And others, it's the hydrogen bonding, but it just has a lot of hydrogen bonding associated with it. And therefore, the stronger the IMFs, the lower the vapor pressure. That is, what we say, the less volatile it is. The weaker the IMFs, the higher the vapor pressure, and the more volatility. And so this is lower volatility. Volatile just means, you know, how it evaporates, lower volatility. The weaker the IMFs, the higher the vapor pressure. And so if these molecules aren't very sticky, then they're easy to vaporize. And therefore, they're going to generate a higher pressure. And we call it higher volatility. And so this is just showing the extent. So here we have net vaporization. And then we hit a peak here where it just stabilizes. Now, we can generate something called a vapor pressure curve. So let me move this slide out. I don't really like the order it's presented. So this liquid, this is what we call liquid vapor equilibrium. You know, when we have the vaporization and the condensation. It's a dynamic equilibrium. We have the equilibrium vapor pressure. It's also reversible. That is, condensation is the reverse of vaporization. And so those are some points of dynamic equilibrium. Let's bring this up here too. Temperature is going to have an impact on the dynamic equilibrium here. This is called a, does anybody remember what this is called? This curve, you've seen it before, gases. But it was a super long time ago. Maybe you completely forgot.
What's the first letter of the name?
M.
M?
Yeah, M-A-X.
Max and Min?
No, not Max. Maxwell. Maxwell hyphen Boltzmann. Maxwell Boltzmann distribution. You don't need to know that before. This is what we call a population distribution. So if you have a glass of water, not all the water molecules are moving at the same kinetic energy. Some are moving at higher energy, some are moving at lower energy. This is for 25 degrees C. So water at 25 degrees C shows a population distribution of energies. The total population is the area under this curve. And so you have a small fraction of molecules with high energy. This energy cutoff here is the energy required to vaporize. So as long as the molecule has a higher energy than this cutoff, it can vaporize off the surface. That means the bulk of the water molecules do not have enough energy to vaporize off the surface. So the bulk will stay here. So this is just showing. Now, if the molecules are stickier, then the energy cutoff goes up higher. If the molecules are less sticky, the energy is here. So if it's easy to break apart the molecules and the energy is low, that means the population fraction that can vaporize is high. That means it's more volatile. And if the cutoff is higher, that means the molecules are very sticky. It's hard to break them off. And so the energy cutoff changes with how sticky or how strong the intermolecular forces are. They also show another Maxwell-Boltzmann distribution here. Let me show you this one. Just want to reorganize. This is what happens when you increase the temperature. When you increase the temperature, it shifts the whole population to higher energy. So this is, let's say, room temperature here. The blue curve is a higher energy, so the whole thing shifted. If the whole thing shifts to higher energy, we're going to get a bigger population. So the blue population is higher here, and so you're going to get more evaporation occur, more vaporization than the red curve. The red curve is lower temperature, the blue curve is higher temperature. We can graph this. And we can come up with these. And so these are all the concepts wrapped up in one. One is how sticky are the molecules. So in this case, water is the stickiest. So water is going to have the lowest vapor pressure for a given temperature. So let's say if we're looking at minus 20 degrees C, water is flatlined at the base. So this red one's much more volatile. You know, if we look here, which one has the highest? So if we're at this temperature, water is very low vapor pressure. The green one is higher, and the red one is very high. There. And it depends on how sticky the molecules are. And so the stickier the molecules, the lower the vapor pressure. The less sticky the molecules, the higher the vapor pressure. You've seen here, this red one shoots way up, and the green and the blue. This also shows the impact on temperature. You know, as we increase the temperature, the population of molecules that are energetic enough to vaporize increases. And so here we can see the population increase. The mathematics of that is dictated by the Maxwell-Boltzmann curve, which I showed. I didn't show you the math. I just showed you the curve. But anyway, the more volatile it is, the lower the boiling point. And so this rapidly gets up to 760 at only 34.6 degrees C. So diethyl ether boils at a very low temperature, almost room temperature. Ethanol boils at a little higher temperature, It's less volatile, 78.3 degrees, and water is the least volatile of these three liquids, and boils at 100 degrees C here. That's the normal. You know, at other atmospheric pressures, the temperature changes. So a vapor pressure curve, these are all called vapor pressure curves. The vapor pressure curve is easy to determine the boiling point at any pressure. And so let's say the atmospheric pressure were 600, then the boiling point of water would be here, 90. The boiling point of ethanol would be here, about 75. The boiling point of diethyl ether would be here. Now, diethyl ether only has a dipole. You know, these oxygen-carbon bonds are polar, and so there's a dipole pointed down. Ethanol has hydrogen bonding, though, and so ethanol has this OH, like water, OH, and so ethanol, like water, can hydrogen bond, so its boiling point's going to be fairly higher than something that can only do dipole. All three of these have London forces as well. This one's going to have the strongest London force because this has the most electrons. It's hard to compare sometimes the London force and the other forces because of size, that is, the number of electrons can impact things quite significantly. All right, so boiling point, we talked about that. We also have something called heat of vaporization. Heat of vaporization is the amount of energy required to vaporize, let's say, a mole or a gram of liquid. And so it's going to cost you energy to vaporize. That is, to break all the IMFs. Excuse me. Yes. And so we could vaporize this by heating it up. And that's the heat of vaporization. The heat of vaporization for water is, you can find in a table easily. And we're going to use that a little bit later. It turns out the heat of vaporization, it costs you energy to vaporize, is exactly opposite the heat of condensation. So heat of vaporization is endothermic, but when we condense water, we lose all that energy because energy is conserved. This is the first law of thermodynamics. So if it costs you this much energy, you're going to get that much energy back. And so when water condenses, it's going to get, it's going to release heat. When water boils, it consumes heat, consumes energy. There are some other properties, viscosity is the resistance to flow. So the more sticky the molecules are, the stronger the IMFs, the more resistant to flow it is. It's like syrup. Syrup versus water. Now, syrup flows very slowly, so we say it has high viscosity. It's strong. Syrup has lots and lots of hydrogen bonding interactions. There's also something called surface tension. Surface tension is, you have to break those IMFs. In other words, you have to break apart the sticky water molecules in order to break the surface. And so there's lots of demos of this, that people do for surface tension. So you could float objects that are heavier than water, that is more dense than water, on the surface because it costs you energy to break apart the surface. So if you get staples, for example, and then place them on the surface gently, you could get the staples to float. So I got two staples to sink and then one staple to float. And so there's a floating staple here, but the staple, oops, it just dropped. The floating staple is due to the surface tension of water. That is, it costs energy to break the surface. So I have a floating staple there. I don't know if you can see it. But there's one staple floating on the surface. This is something you could do at home. There's a magic trick. Have you seen this magic trick? I can command the staple to drop. I'm going to command the staple to drop when the drop of Windex hits. So I'll put a drop of Windex on the inside surface of this, and then I'll command it drop. You see, once the Windex hits the surface of this, do you know what it does? The Windex interferes with the hydrogen bonding interactions here, it weakens the surface tension. When it weakens the surface tension, the stable drops. So you make it drop on command by just letting the drop of Windex hit the surface. The Windex is called a surfactant. Surfactants, like cleaning agents, they want to lower the surface tension of water. There's reasons for that. For cleaning, it makes things easier to clean. So the surface tension here, let's see, shown in this slide here. And that is because surface tension is a resistance to form more surface molecules. Surface molecules, this is showing the difference between a surface molecule and an interior bulk molecule. Interior molecules are really surrounded by other water molecules. And so these are the lowest energy water molecules here because they're completely encapsulated by other water molecules and they're all stuck to one another. Whereas if you're on the surface, you know, what's holding you to the liquid? You don't have a sphere of water molecules holding you. You only have a half sphere of water molecules holding you. And so this one is less stable. This one's easier to break off than this one. So this one is less stable. That means it's higher energy. So the more surface water molecules you have, the higher energy the system is. And so nature tries to minimize energy. So it's going to try to minimize creating more surface molecules. Surface molecules are less stable. And so as a stable sits there, you know, it just sits there. But if it breaks the surface, it creates more surface water molecules, which increases energy. So there's going to be a point where the gravitational energy is less than the energy required to break the surface. Of course, you could help it along by agitating the surface and creating more surface water molecules by agitating it, or by lowering the strength of the surface tension. Now I can't, you know, once I put Windex here, I can't get I won't be able to, I mean, you could tell your friend, okay, that you can put a staple on the surface of water, but they can't, you know. And now it's going to be impossible. There's no way you're going to be able to float a staple on here with a drop of surfactant. This is called a surfactant. Surfactants are designed to lower the surface tension. So once the surface tension has been lowered, then forget it. You're not going to surf. And so you can make a little bet if you want for that, because they won't be able to still float it. But it would be kind of tricky and not fair. But anyway, going to this, we're looking at intermolecular forces here. And so the intermolecular force is weakest to strongest. So liquid mercury would have the strongest, ethane would have the weakest. And so when we look at the vapor pressure, the stronger the intermolecular force, the lower the vapor pressure. You don't need to know the numbers here. The weaker the intermolecular force, the higher the vapor pressure. And so we just summarize it like this. So this is just, in fact, just ignore these numbers, basically. And then this is just increasing vapor pressure as we go down. Heat of vaporization is the same thing. The only heat of vaporization we might be interested in is water. But the stronger the intermolecular force, the more heat it's going to require. The boiling point, the stronger the intermolecular force, the higher the boiling point. So this is increasing delta H of vaporization. That's the symbol we use. And this is increasing BP, boiling point. And so the heat of vaporization and the boiling point follow the intermolecular force. However, the vapor pressure is opposite the IMFs. I talked about normal boiling point. That's when we have normal pressure. You know, the abnormal one is just when we have any other pressure. When we have boiling, it's called a liquid-vapor equilibrium. That is, the water just spontaneously boils. So this is boiling here. A liquid, in this case, water, boils when its equilibrium vapor pressure equals atmospheric pressure. So you have the atmospheric pressure pushing down, and then you have the vapor pressure pushing up. And so once they're equal, then we get boiling. It depends on how heavy the atmosphere is that's pushing down on this surface over here. So we have P atmosphere pushing down, and then we have P vape pushing up. And when these two are equal, then we get boiling. Water has some, well, they call them unusual properties, but these are the properties of water. The unusual properties of water, this is for life. And this is why when they're looking for life on other planets, they look for water for one, because if it weren't for these properties, the life wouldn't exist on Earth. One of them is a relatively high boiling point, 100 degrees C. Water has fairly high surface tension, higher heat of vaporization, lower vapor pressure, higher viscosity, dissolves many substances. It's a liquid at room temperature, pressure. Solid floats on gas. Solid ice is less dense than liquid. These you don't have to memorize. But those, if you're taking biochemistry, this would be chapter 1 of biochemistry, the unusual properties of water, and then you have to know them quite well. But for us, just know that water is special. Water is tetrahedral, EGG, electron group geometry. And lone pair here, lone pair here. One lone pair is wedged out, and the other lone pair is wedged in, or dashed in. It's a tetrahedral bond angle, which is 109.5, but the two lone pairs here and here compress the bond angle to 104.5, about a 4-degree compression. It's very polar. As oxygen is quite a bit more electronegative than hydrogen, and so we get these dipoles. These bond dipoles add up to a net molecular dipole. The net molecular dipole is straight up and down here. And it's going to be negative at the top, positive down here. The net dipole, the molecular dipole, is equal to the sum of the bond dipoles. So that's water. And in solids, we have crystalline and amorphous. This was supposed to be in blue here. The difference between a crystalline solid and amorphous solid is that the amorphous solid lacks what we call long-range order. It lacks long-range order. Whereas crystalline solids have long-range order. These are very well organized. Amorphous are a little bit more disorganized. Let's see if we have a shot of a crystalline versus amorphous. This would be more of amorphous solid here. Now, it's hard to predict where this polyethylene will be over here, which way it goes. Whereas something like silicon is very well ordered. It's easy to predict where the atoms will be as we extrapolate out. Aluminum is also very well ordered. Sodium chloride is also very well ordered. Those are all quite good. So the difference is, can you extrapolate its position? And so something like this, it's hard to extrapolate because it's going all over the place. Crystalline orders have this well-ordered, crystalline solids have this well-ordered structure. So typically, like ionic crystals, they cleave. So what you take is a big crystal and make lots of baby crystals from this. They all look the same. Whereas amorphous solids, you can't take a big amorphous solid and make a whole bunch of baby amorphous solids. I guess you can, but they don't look the same. They're all different. These are conchoidal fractures, what we call here. And you can't really predict them so easily. Whereas here it's so easy to predict. And you have these gemstone cutters that are very good at cutting gemstones because they know the planes for the crystal. Whereas you aren't going to have this. These are going to break up into odd shapes in amorphous. And so there's a structural difference there. If we look at types of solids, this is crystalline and amorphous solids. We have ionic molecular, covalent, network, metallic. This depends on the bond that holds them. Ionic crystals, we have ionic bonds. Molecular crystals, we have IMFs, intermolecular forces. Covalent network solid is like an ionic lattice, except made with covalent bonds. And the metallic crystals, covalent and ionic bonds are very strong. IMFs are weak. So ionic crystals and covalent network solids have high melting points. Metals, it varies. You have weak bonds in metals and strong bonds in metals. And so the boiling point varies, or melting point. We should consider melting points as a solid. And so the stronger the bonds that hold this together, the higher the melting point. The weaker the bonds that hold this together, the lower the melting point. So melting point gives us a good indication of strength. Ionic bonds are typically strong, so the melting points of a lot of these ionic solids are very high. It's hard to melt. This one, what does that look like to you? This one is, I don't know what that is. That could be lead sulfide. These are molecular solids here. These are crystalline also. These are tiny crystals of sulfur. These molecules stack together in neat arrangement. And these molecules are only held by dispersion. Dispersion is another name for London forces. I forgot to write that down. But these are only held together by London forces. There's no dipole. These are just sulfur rings of these sulfur atoms. This is a sulfur chain, what we call a polymer. So this is more rubbery. And this is amorphous stuff. It's hard to predict because it's just like a spaghetti noodle. Whereas this is crystalline, it's easy to predict. It's going to be because we're going to have another molecule here, 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 etc. Often three.
Is that supposed to look like an iceberg?
This one?
No.
This one? No. They just made it into a little volcano or iceberg. They could take on different shapes. These are covalent lattices. These lattices extend off in 3 dimensions, but are held by covalent bonds rather than ionic bonds. These are examples of covalent lattices: quartz, citrine, amethyst, etc. These have extremely high melting points because these have strong covalent bonds holding everything together. Because the quartz's melting points over 1,000 degrees Celsius, 2,000 Fahrenheit. Metals have wide ranging, depends on how strong. Aluminum doesn't have all that high of a melting point. There's some that melt near room temperature, like cesium, and some that melt at very high temperatures, like platinum. It's metal. A lot of the properties are dictated by the bonds that hold them together. Like ionic bonds are strong, therefore they're high melting. Molecular are IMFs. Like for example, C10H8, that's probably all London. I2 is all London. These are low melting. Covalents, like these covalent, like quartz and diamond, are very high melting. So very high melting, that means these covalent ones here are typically stronger than these ionic ones here. These are high melting, these are very high melting. And the metallic are wide range of melting points. Tungsten's very high, much higher than, let's say, copper, iron. But there are other properties that we're interested in. Like ionic solids are water soluble because, they're quite polar. They got monopoles that can be attracted to dipoles. They're also brittle. They conduct electricity when they're melted or dissolved. We talked about electrical conductivity earlier. Whereas molecular have low melting. These are soluble in nonpolar, unless it's a polar molecule. If it's a polar molecule, then polar solvents like water. If it's nonpolar, then nonpolar solvents like oil are better. They're non-conductors in pure state. There's no charge. Now, network covalent, these don't conduct either. And so these are non-conductors. There's potential semiconductors there. Semiconductors we really haven't talked about, but semiconductors somewhere between an insulator and a conductor. It's a semiconductor. These are insoluble in all solvents. Even though silicon dioxide like this or quartz is polar, it's insoluble in polar solvent. It's insoluble in nonpolar solvents as well. It's just hard to break the covalent bonds. Metals have additional properties. You know, metals are insoluble as well, although some metals react with water violently, like lithium. Sodium, potassium does react violently with water, but that's not being dissolved. This dissolution or dissolving is a physical process. But the metals are also malleable, which means you can shape them into different shapes. Ductile, which means you can draw them into wire, and they're good electrical conductors. The metallic. Now, this is kind of a long chapter. So what we're going to look at is energy and change of state. And we're going to look at energy and temperature. So when energy is added, like we can melt things, we can vaporize things, etc. So I'll talk about this in a second. Yeah. So let's say we want to melt something. Let's say I want to melt silver. Melting silver is, the temperature is going to be 962. And when we melt silver, it's going to cost you 105 joules of energy to melt a gram. This is called heat of fusion. Heat of fusion is heat of melting. If I want to boil silver, I'm going to have to raise the temperature to 2162 degrees C, and it's going to cost me 2.4 kilojoules per gram. Kilojoules, that's more than 1,000 times. That's about 2,000, more than 2,000 times the amount of energy. This is joules, this is kilojoules. And the reason is because when we vaporize, we have to break the particles apart completely. Whereas if we melt it, we don't have to break them apart completely because the liquid, all the particles are still stuck to one another. But in a gas, a vapor, all the particles are separated from each other. And so heats of vaporization are a lot higher than heats of fusion. And therefore, the units we use are different. They're about 1,000 times higher. So rather than joules per gram, we do kilojoules per gram. About 1,000 times higher. More energy. So when we look at melting, you know, like copper. Copper's melting point is 1084, and its heat of fusion, that is heat of melting, is 206. Its boiling point is 2927, and its heat of vaporization is 4.7. This one's an important one, water. Water melts at 0 degrees C, and it has a heat of fusion, that is heat of melting of 333 joules per gram. And water boils at 100 degrees C, and it has a heat of fusion of 2.26 kilojoules per gram, which would be 2,260 joules per gram. So water is a pretty important one. We'll see. And so we'll probably end up using that. So how much energy is needed to vaporize 188 grams of the liquid at this heat of vaporization? So they give us a heat of vaporization 1.13 kilojoules for every gram. So if I have 180 grams, it would be 180 times that. So we could use dimensional analysis for this. 180 grams times 1.13 kilojoules per gram. That would be it. Or we could use this equation here. This equation, we're going to come up with a generic equation. And that is, whenever we have a phase change, actually, let's get the answer here. 212 kilojoules. Whenever we have a phase change, the amount of heat Heat is given the symbol Q. Q. We have two types of ones. We have phase change. Like vaporization. Fusion or melting. Condensation. And freezing. Temperature is constant. That is, the temperature doesn't change. When we vaporize water, when you boil water, does the temperature change or does it stay 100 degrees C? When you melt ice, does the temperature change or does it stay 0 degrees C? And so temperature is constant. That's what that's supposed to say. Temp is constant. I.e., that is, it's you know, the boiling point, melting point, etc. And we get this equation. Q is equal to the amount times delta H of the phase change. Amount is usually in grams, so they just have it as M times delta H of the phase. This is for phase change. However, if we're looking at heating and cooling an object, heating / cooling an object, so there's no phase change here. Then what we have is we have this. Q is equal to the amount times C times delta T. Or if we use mass as the amount, then Q is equal to M times the specific heat times delta T. MC delta T. So the energy, what does the energy or heat go into? Up here, the heat is used for the phase change. Heat is used to change state. State being gas, liquid, solid. Here, the heat is used to warm or cool the object. C is called the specific heat. Delta H is called the heat of vaporization, fusion, etc. In other words, heat of the phase change. Sorry, I ran out of room. So, when we look at the specific heat, the specific heat is given as a ratio of joules per gram per degree C. So this is a temperature in there. It's not just joules per gram. And these are typically in joules per gram, not kilojoules per gram per degree C. And the way we read this is, like, for example, water. Water has a specific heat of 4.18 joules per gram degree C, or 1 calorie per gram degree C. And the way we read that is, if you have a gram of water and you want to warm it up by 1 degree C, it's going to cost you 4.18 joules. So 4.18 joules is required to warm up a gram of water by degree C. Take a look at the specific heats here. Water has about one of the highest specific heats, if not the highest. The others have very low specific heat, like gold. Solid gold, its specific heat is only 0.13. So you can warm up gold very, very easily. To warm up 1 gram of gold by 1 degree C only costs you 0.13 joules. To warm up 1 gram of liquid water by 1 degree C costs you 4.18 joules. So what we say is gold has a very low specific heat. It warms up and cools down rapidly, whereas water has a very high specific heat. It warms up and cools down much more slowly if you're inputting heat energy. So we can do some calculations. How much energy is required to change the temperature of 25.0 grams of water from 10 degrees C to 50 degrees C? So we're going to use this. Q is equal to MC delta T. Delta T is T final, 50 degrees C, minus T initial, 10 degrees C. So it's plus 40 degree C temperature change. And so we plug that in here. So it'd be plus 40 degrees C temperature change. We have 25 grams. The more grams we have, the more energy. So 25 grams, the grams cancel, the degree C cancels, that leaves us with joules. So it's going to cost us 4.18 kilojoules worth of energy, or 4,180 joules worth of energy. So this is, a long chapter. So we have this at the end. So what we're going to do is we're going to do a change in temperature plus a change in state. The change in temperature, the heat's used to change the temperature, versus a change in state, the heat's used to change its state, solid, liquid, gas. So this tells us a sequence. If you have a solid, the first thing we need to do is warm it up to its melting point. Once we hit the melting point, then we use the heat to melt it. Once all of it's melted, then we use the heat to warm the liquid up. Eventually the liquid hits its boiling point, and then we use the heat to boil it. Once we boil all the liquid, then the gas will become hotter. And so we can summarize it here. This is a heat graph. And so as we add heat, we're going along the x-axis here. There's the heat energy in joules. So we start off with the solid here, and the first thing we do is we heat it. As we heat the solid, all the energy is being used to warm up the solid. And it's going to stop once we hit the melting point. Once we hit the melting point, then all the energy is not used to increase the temperature. All the energy is used to melt, that is to break the IMFs or to break the bonds holding it together. And so we melt it. But once we melt all of it, then the energy is used to warm up the liquid up to its boiling point. Once we hit the boiling point, then the energy is used to boil the liquid. And this is a lot of energy because boiling is more energy intensive than melting. Because in boiling, you have to break the particles completely. But once we break apart all the particles completely, then we have a gas, and the energy is used to increase the temperature of the gas. And so what we do is we break this into different parts. It depends on how far we're going. So this is called Q1 here, and this would be Q2. This would be Q3, Q4, and then Q5. Each of these takes a different equation. So when we heat something or cool something, then Q is equal to MC delta T, where C is going to be the specific heat of ice. But when we melt or do a phase change, then Q is equal to the amount times delta H. This is going to be delta H of fusion because it's melting. Okay, once we heat everything up, then we're going to go back to MC delta T. Here. This is C of ice. This is C of water. That's the specific heat we use. Okay, when we boil it, it's just M times delta H. Now boiling is vaporization, so we'll just call it delta H of vaporization. And then over here, this is a gas, so we're just heating up the gas, MC delta T, where C is for the gas. And so it depends on how hot you're going to get this and how many grams, and that's going to dictate how much energy you need for that particular step. So we calculate it by sketching a graph like this and then mark it. So let's take a look at an example of this. Excuse me. Calculate the total heat transfer on 19.6 grams of ice initially at minus 12 degrees C. So we start at minus 12 degrees C, ice. And the first thing is we're going to heat it. So as we heat it up, the ice is going to warm, but it's going to hit a max temp. The max temp of ice is 0 degrees C because at 0 degrees C the ice starts to melt. And so the first step of this is warming up the ice. Well, how much energy does that take? And so we're going to calculate it here. Actually, it's probably here. So we're going from A to B. A to B is minus 12 to 0. So we're going from minus 12 degrees C to 0 degrees C. And if we're warming up ice, it's MC delta T. M is the mass, 19.6 grams. C is the specific heat of ice. The specific heat of ice is 2.06 joules per gram degree C. This comes from the table. Delta T is the final temperature minus the initial temperature. So 0 minus a minus 12 degrees C. And then they convert it into kilojoules. And so we get 480 joules or 0.48 kilojoules. That's how much energy the first step cost. All right, when we go from B to C, the energy is not used to warm things up. The energy is just used to break apart the solid, convert it into a liquid. And so how much will it cost to melt all the solid? Well, it's a different equation for that one. And so when we go to B to C, here, it's for a phase change. For a phase change, we use this equation, M times delta H of the phase change. This is a fusion, which is melting. So M times delta H of fusion. Well, M is the mass, 19.6 grams. We're going to melt all of it. And delta H of fusion, we get off the table. 333 joules of energy are required to melt each gram, and then convert it into kilojoules. So this step costs 6.53 kilojoules. So it's a bit more. You know, this is just warming up the ice from minus 12 to 0. This is melting it. And so we got to break some of the IMFs holding it together. All right, once we melt all of the solid, it's just liquid. And any heat that's given to the liquid will warm it up until it hits the boiling point. And so we're just going to warm this up to the boiling point. What's the equation for that? And so this is going to be C to D. For C to D, we have the MC delta T once again. M is the mass, 19.6 grams, except C, this is specific heat of water. We're warming up the liquid water, which is 4.18 joules for every gram degree C. And then we're warming it up from 0 degrees C initial to a final of 100. And so 100 minus 0 is plus 100, and then converting it into kilojoules. So to warm up the liquid water from 0 degrees C to 100 degrees C, this is for 19.6 grams. It's going to cost us 8.19 kilojoules worth of energy. All right, excuse me. Once we warm the liquid water up to its boiling point, then it's going to start to boil. So all the energy is going into boiling it, not increasing the temperature. And so the temperature stays flat, i.e. constant. And so let's look at DE next. The heat required to boil it is equal to the amount, 19.6 grams, times delta H of vaporization, 2.26 kilojoules per gram. This is going to give us the biggest energy total, 44.3 kilojoules worth of energy required to boil all that water. And so that's actually the most significant so far. The final step of this is once we boil all the liquid, we have gas, and so it's just warming the gas. Warming the gas is mc delta T. Whenever we warm or cool, it's the same equation, mc delta T. So E to F, mc delta T, but this specific heat is for steam. So it's the same, 19.6 grams. We're heating it up to 115 degrees C from 100. And so this is 2.0 joules per gram degree C. Converted into kilojoules, we get 0.59. So altogether, if we add up the steps, step 1, step 2, step 3, step 4, step 5, the total energy comes out to 60.1 kilojoules worth of energy required to do that. And so there are two equations. You just have to figure out what part of the graph you're on. Okay, any questions on that? All right. Let me dip into chapter 16 then here. So we just did solids, liquids, and gases. Next we're going to take a look at solutions. This is going to look at liquid solutions. We have gaseous solutions like air, solid solutions like alloys, but we also have liquid solutions like aqueous salts. A solution is a homogeneous mixture, and the components are uniformly distributed. It exists in three states, so gaseous solutions, liquid solutions, solid solutions. We're going to spend most of our time looking at liquid solutions. The dispersed particles are very small and do not settle from standing. That is, if you have a glass of salt water, the salt doesn't sink to the bottom. You know, the salt particles themselves are very small, and they're kind of constantly suspended due to the kinetic energy of the water. Two solutions made up of the same substance may have different compositions. That is, one might be more concentrated, the other might be more dilute. So the concentration can have an impact on properties, certain properties like density, etc. When we have a solution, there are two components to a solution. There's the solute, which is the minor component, the smaller amount, and the solvent, which is the major component. And so those are two terms. There are more terms that you have to deal with in addition to solute and solvent. So here we have some salt here and some water. In this case, the major component is water, that's solvent, and the salt is the minor component here. And so the solute is the salt, the solvent is the water in this solution, this mixture. One of the things we're interested in is the concentration. You know, is it concentrated or is it dilute? And what is the concentration specifically? Here we can see some dilute copper solution, copper tube. Here's a more concentrated copper tube. You can see the color difference here. This is more dilute, so it's a lighter blue. This is more concentrated, it's dark blue. There's some other chemistry happening here, which I'm going to skip for now. Some other terms that we associate with solution are solubility. Solubility is the maximum amount that will dissolve in a given amount of solvent. We can talk about saturated solutions. Saturated, we've maxed out. We can't dissolve anymore. And unsaturated, we can continue to dissolve. And so there could be limits. If there are no limits, then we call it miscible. Miscible means that it's 100% soluble. No limit. Whereas normally we do have a limit. So for example, sugar and water, you can't dissolve an infinite amount. However, alcohol in water, you can. Alcohol is miscible in water. And therefore, any proportion is it's fine. Immiscible means they're insoluble in one another. So this would be oil and water. Oil and water are insoluble in one another. And so those would be considered immiscible liquids. Saturated, miscible things have unlimited solubility, but most things there's a limit, and that limit is the solubility. And that solubility is going to determine what is saturated. And so if we're at the limit, it's saturated. But sometimes what we can do is we can go over the limit. We can go over the limit and become supersaturated. Supersaturated means we're over. And if it's supersaturated, what happens is the excess solute can crystallize out like this. And so this is a scenario where we have too much dissolved solute. And we can get this scenario usually by heating it up and cooling it down. This is why there's water here. If we heat this up and then cool it down, usually hot solids are more soluble. When you cool it down, they become less soluble, but sometimes forming the crystals are hard. And so one of the processes in forming crystals like this is crystallization. But for crystallization to occur, you have to pack together the particles in just the right order. Well, one way you can help it is by introducing a seed crystal. This is called a seed crystal. The seed crystal drops in here and then provides a template for the crystals to grow. So that's what's being shown here. Okay. Here we have two miscible liquids, octane and carbon tetrachloride. They're miscible. Miscible means they can be dissolved in all proportions. Here you have immiscible solids. Immiscible are 0% solubility. And so we have gasoline on the top, water on the bottom. So this is oil and water. They don't mix. So let's look at solution formation next. When we do solution formation, there are some processes that occur. One is we have to break apart the solute. This is sodium chloride, so the sodium ions and the chloride ions have to break apart. Two, we have to break apart water molecules to make room for the sodium and to make room for the chlorides. Three, we form what we call hydrated ions or solvated ions. These spheres of water molecules surrounding them, if you look carefully, this is a chloride. The hydrogens are pointing towards the chloride. This is a sodium. The oxygens are pointing. So what we set up is what we call an ion dipole attraction. An ion dipole attraction can be very favorable. Here. Excuse me, this is stronger than the dipole-dipole attraction because an ion is a monopole, it has a full charge. And so this is a negative charge over here. And this one down here is a positive charge. So that's better than a partial charge. Dipoles are usually dealing with a partial charge. And the water molecules are positively charged, but the ions are fully charged. And so those ion dipole attractions can be quite good. Yeah. But essentially, this is a solution process here, as depicted in this slide. Forming a saturated solution is just like forming a saturated gas with humidity. Initially, there's nothing dissolved, so this green stuff starts to dissolve, and we get dissolution. But when we generate the particles in the aqueous phase, they can come back and strike the crystals. If they come back and strike the crystals, then we have this step occurring, which is crystallization. Eventually, we get to the point where, let's say, 4 particles leave, 4 particles crystallize, and we hit a state of dynamic equilibrium. And this is going to form a saturated solution of the salt here. There's certain factors that influence solubility. The strength of the intermolecular forces are important. But also, for gas solubility, the pressure of a gas over a liquid solvent. So let's take a look at a supersaturated CO2 solution. Short one. It's 218.
Hey everybody, how you doing? Hey, have you ever noticed when you put a
So this is what we call a supersaturated solution here. If you buy a carbonated beverage, the headspace here, the gas here, is pure CO2. This gas being pure CO2, the CO2 gets forced in, and the CO2 escapes out. Eventually, we hit a state of dynamic equilibrium. Let's take a look. And go to a different one where they have the bottle. So if we look in here, this is CO2, and the CO2 is going to hit a state of dynamic equilibrium here. So we have a fairly high concentration of CO2 here that's going to force CO2 in the liquid. Also, some CO2 is going to escape out, and then we hit a state of dynamic equilibrium. But what happens when you open the lid is it goes from pure CO2 to air. How much CO2 is in air? The percentage of CO2 in air is way less than 1%. And so what happens is you go from fairly high, and then most of the CO2 escapes into the air. So you barely have any CO2. So there's no CO2 that's forcing this. And so the amount of CO2 going in is not enough to sustain this. And so what happens is this becomes supersaturated. With CO2. We have way too much CO2 in there. And so what happens is for every 10 CO2s that escape, none go back in. So eventually this is going to go flat. but it's sluggish. It doesn't go flat immediately because of bubble formation. It's sluggish because the bubbles are slow to form, and therefore it could stay sparkling for a while. And so if you order a Diet Coke, it doesn't go flat immediately. It'll stay sparkling for a little bit. But you know what catalysts are? What are catalysts? Catalysts speed up reactions and processes. And so one catalyst for this is Mentos. There are other catalysts that we can use. But what Mentos does is these little candies provide surfaces for new bubbles to form, or nucleation of bubbles. And so if they dump some Mentos in here, you know, right now it's just very slowly going flat. So for every 10 CO2s that escape, none really go back in. So eventually this is going to go flat. But if you want this to go flat more rapidly, this person's going to dump in a whole bunch of Mentos candy, and that's going to create lots of bubbles, in which see what happens. And so we get rapid bubble formation. So that was supersaturated. There was way too much CO2 that could be supported. But it's what we call an unstable state. A metastable state is what it is. It's not going to stay supersaturated forever. Ethylene glycol is miscible in water. Ethylene glycol has hydrogen bonding interactions. This is an ethylene glycol molecule, so you can see the OH here, the OH here. So that's very water-like. So ethylene and water are very similar. And so we have the rule, like dissolves like. Since ethylene glycol hydrogen bonds and water hydrogen bonds, they're compatible. However, oil and water are immiscible. You know, oil is going to float on the surface here, it's less dense. And it doesn't mix even though it drops down here and goes back out. And that is, water likes hydrogen bonding, but oil does London primarily. Water also does London, but it's not significant. And so in order to make room for these oil molecules, you have to break apart a lot of water, which is going to be unfavorable. And so those are immiscible. But we can get an idea of solubility based on this. This is a slide that's out of place. This was supposed to be with the. So a higher concentration of CO2 here, it forces more CO2 in here. So let's say these red ones are CO2. If we release the pressure, then it becomes supersaturated. So if we release the pressure, you don't force as much in, and then it doesn't instantly degas. It takes time. So we release it, it becomes supersaturated, and eventually it becomes just saturated. So if we release the pressure, then fewer are going to go in, but fewer escape. Anyway, so we reach that state of dynamic equilibrium, or the same amount escape. Most things become more soluble with increasing temperature. So you can see that most of these increase the solubility here with increasing temperature. Some are the opposite, but most of that. And that makes sense, because if you want to dissolve more sugar, you want to dissolve more salt, heat it up. However, that doesn't work for gases. If you heat up your sparkling water, it's not going to make it more soluble, it's going to make it less soluble, and it's going to get even more flat more quickly. All right, this is one of the calculations you need to do in the lab, and that is calculate the percent by mass acetic acid. So this is just grams of acetic acid over the total mass. The total mass would be grams of solution times 100%. The mass of the solution is the mass of the solute plus the mass of the solvent. It's the combined mass. And so it would be the total mass of all the solutes present. So that's common for solutions, but there are also other units that are common. Here's an example of percent by mass. 125 grams of solution, so that's the total. Was evaporated to dryness. 42.3 grams of solute was recovered. So there are 42.3 grams of solute for every 125 grams of total solution. So it's 33.8% solute by mass. This particular equation. Here, another percent by mass calculation. You are to prepare a 2.5 times 10 squared, 250 grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? The density of water is 1.00 grams per milliliter. And so we know we have 7%, so that's 7.00 grams of pure sodium carbonate for every 100 grams of solution. That's what we want. We want 250 grams of solution. So 250 grams of solution, and the solution contains 7% sodium carbonate by mass. That means we're going to need 17.5 grams of pure sodium carbonate. So this is just dimensional analysis here. Out of that 250 grams of total solution, 17.5 grams of sodium carbonate. The rest will be water. So we'll have 233 grams of water and about 17 grams of sodium carbonate. That's going to give you 250 grams. So at a density of 1, 233 grams is 233 milliliters of water. So that'll be another sample calculation here. Another unit that we use quite frequently is molarity, moles per liter. We can calculate molarities. Calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide. So we just go from 15 grams of sodium hydroxide to moles of sodium hydroxide. So 15 grams to moles. And it's moles per liter of solution. We have 100 milliliters of solution here, so we have that many moles per 100 milliliters, which are 0.100 liters. And just take the moles and divide it by the liters. 3.8 molar. Molality, I'm going to skip. The molality is defined differently. It's given the symbol little m, and it's defined as the moles of solute per kilogram of solvent. And so different units here. The advantage of using molality is it doesn't change with temperature. The number of grams isn't going to change with temperature. However, the volume will change with temperature. So molarity is temperature dependent, whereas molality is temperature independent. And so that's why people use molality. But molality is a bit more hassle in stoichiometry calculations, so we don't really use it as much. We also have another concentration unit called normality. If you do a lot of titrations, you might use normality. We aren't. Normality is defined as the equivalence per liter of solution. Equivalence is how it reacts. And so I'm going to skip normality. Skip normality, skip. And really focus just on these two. These are the two of the most common. Percent doesn't change with, percent by mass doesn't change with temperature. And molarity, because the volume changes slightly, temperature, molarity does change with temperature. Molality, we're going to kind of skip that. Normality, we can skip that. Molality is more complicated because it's per kilogram of solvent. Not solution, but solvent. Okay, We also have something called solution dilution. This is a solution dilution equation. Solution dilution is common practice in the chem lab. You know, because normally you buy concentrated stuff and then just dilute it. So it's like soap. If you buy liquid soap, you buy the concentrated stuff and then dilute it. You can save money that way sometimes. And so we buy the concentrated acid, we buy the concentrated base, we buy things in concentrated form and then dilute it to the concentration that we need it. When we do that, we'll use the solution dilution equation, which I say M1V1 is equal to M2V2. And so we'll take the concentrated stuff here before and dilute it, just add more water. And so if you look at the solute, 1, 2, 3, 4, 5, we still have 1, 2, 3, 4, 5, but now we have a lot more water. And so this looks like to be diluted by a factor of 3. So it looks like we have 3 times the volume. If we have 3 times the volume, then the concentration is 1/3 the previous. And so this, if this was 1 molar, this would be 1/3 molar. This is a 1 to 3 dilution. 1 part diluted to 3 parts. 1 to 3 dilution gives us dilution factor of 1/3. Sometimes the dilution factors aren't so simple. So this is a standard solution dilution here. This is the concentrated stuff. So we pour the concentrated stuff in here and then just add water to dilute it. And so concentrated is diluted. Then we look at for the dilution factor, like how many times. So it looks like we added 100 and diluted to 1,000. So that's a 1 part to 10 part dilution. And so in other words, this will be 1/10 the concentration. So if we start off at 0.100 molar, this should be about 0.01 molar, 1/10 that. So 1 to 10 dilution. Those are in your head calculations, but you can also do this on paper. Here's an example of doing this on paper here. How many milliliters of commercial hydrochloric acid, which is 11.6 molar, should you use to prepare 5.5 liters of 0.500 molar hydrochloric acid? So we're taking the 11.6 molar and diluting it to 0.500. And they want to know how much of the concentrated stuff do we need to make 5.5 liters worth. And so the concentrated and the dilute. So we want the volume of the concentrated. So that would be V1. And then we plug in the numbers and you get V1, the concentrated, which would be 237 milliliters. And then what we do is we put 237 milliliters in the container and dilute it to 5.5 liters. That would give us our correct concentration. So we'll take a look at that later. The last part of this chapter just deals with stoichiometry. And we've already done some stoichiometry with using molarity as a conversion factor. So it's just molarity is in moles per liter. And so we did the titration problem. That's one of the big applications of this. So stoichiometry using molarity. There's actually more. So I'll stop here. Well, this is probably. We'll continue later.
I have a question.
Yes.
Well, we have, how many exams are we going to have in the upcoming weeks? Because we have this new unit, and then we have the final exam. Is it going to be 2 exams or just 1?
How many exams?
Yeah.
We have the final exam at the end.
So then,
And then,
this is going to be on there along with everything else?
no, this is, we have the final exam plus exam 4.
Okay. So that's 2?
Yeah.
All right. Exam 4 is next week?
Exam 4 is next week.
Okay. Thank you.
you.